Hello Year 13. I'm going to use this video to introduce to you the next chapter in M2. It's nice and exciting. It's on projectiles. So I'm going to send you the link to this GeoGebra, which is very fun to play with. I suggest you spend hours of fun on this. I mean, who needs a PS5 when you can play about with mechanics? So how it works is we have this particle down here fixed at the origin. We can assign it various parameters as to how we're going to fire it. We can set the angle and we can set the velocity. Now, the velocity is going to be set at a different angle to what we'd expect. So using kind of prior knowledge, we can split that into its vertical and horizontal components. I'm going to call those Vy and Vx respectively, right? In the x direction, the velocity, and then the velocity in the y direction for Vy. Okay, so let's set it back to what it was. Let's put it down at 20, keep it as nice numbers. Acceleration is going to act on this particle as it flies through, and that's going to be due to gravity. We'll keep that as 9.8, which is our favourite number g. I can also change the initial height of this particle, and a lot of questions we're going to see are going to involve initial heights, but for now we'll keep it back down on the ground because that's where it's the safest. Right, if I'm going to project this particle then, it's going to be released out into space and drop down, and we can imagine the shape it's going to have as it travels through. And hopefully we know its name. So let's fire it off and see what we get. Okay, so clearly we get what we call a parabola. So our main focus of this chapter is going to be this shape and what kind of features it has. And we're going to derive some nice formulae for it as well. So we're going to be mostly interested in things like this point up here, its maximum height that we can attain. And then also, we tend to be asked about this point down here, which is where the particle reaches the ground. Okay, the two very important points. So I'm going to reset this back to where it was, and we're going to concentrate on what's happening and what happens to the velocity first of all, because that's quite an important thing to know what's going on there with. Okay, so when I release this particle again, I want you to first concentrate on the Vx component, right, the horizontal velocity. So if we fire it, you'll notice it's staying exactly still, right? The velocity in the horizontal direction is absolutely constant. And that's because there's no forces acting on it in that direction, okay? The only force acting on it is gravity, and that's acting downwards. So again, reset. So we're going to note in a minute that Vx is constant. If you now track Vy as I release it, you're going to notice what happens to that, and that's actually going to change. So it starts pointing up, and you notice that gravity is pulling the vertical velocity downwards, okay, more and more and more as it falls through. Okay, so let's make a note of what we just noticed there then. So we've got Vx, okay, horizontal velocity, I'll put that underneath, is constant, okay, which implies that a equals 0. And if acceleration is 0, that means that we can use a very, very simple formula to describe the motion in that horizontal direction, and that's going to be this. So S, which is displacement, is Vx times time. Okay, that's just using bog standard speed as distance over time. Bear in mind that S is standing for displacement there. Okay, so that's straightforward to use. Okay, but then we notice as well that Vy is acted on by gravity, so I'm going to make a note of that as well. Okay, so depending on which direction you're resolving in, typically you're going to want to resolve upwards in the vertical direction. We're going to take a to equal minus g. Okay, that's presuming that we're resolving upwards. So in that case, we've got constant acceleration. So all of our vertical motion is going to involve using suvat. And when I say suvat, I'm going to be mostly be talking about the following three equations because they're the most common that are going to be used. So that's V equals U plus AT. And then our second favourite, which is V squared equals U squared plus 2AS. And then this third one as well. Okay, so I'm going to... there are two others, of course, but we don't tend to see the other two, so I'm going to say these are used most often. So these are the ones to reach for first of all in a question. And also that's vertical, isn't it? There we go. Great, okay, so let's fire off our parabola again. We're going to describe what's going on at these two particular points. Great, okay. So if we're to do a question on this then, we first of all need to make sure that we've resolved into our parallel and perpendicular components, right? Our horizontal and vertical components, I should probably say. So I want the parabola shape, so I'm going to leave it there, but we've got at the beginning of our motion, v for velocity. And then in general, we're going to have different angles here. We're not always going to have 45. So I'm going to put alpha here for our arbitrary angle of projection. And then we're going to have Vx along this way. Now, using SOHCAHTOA, we've done this in previous mechanics chapters. Vx is going to be V, which is normally given in the question, times cos of alpha. Okay, so you can work that out given those two things. And then in the same way, we can work out the vertical component Vy, which is V sine alpha. Okay, bear in mind I'm using subscripts here, right? This isn't a product, it's V sub y, so I can distinguish between the two. Perfect. Okay, so at these nice points, which are the ones we get asked about, we can describe what's going on with velocity. So at this point here, this is the maximum height. And at that very moment, our gradient, if you like, is perfectly flat, which implies that the vertical component of velocity is going to be 0. So that's the kind of main feature of that point there. Okay, perfect. So if you ask to work out that point, that's what you're going to use when you're resolving vertically. At the point down here on the ground, which is where you're smiting your enemies with your missile, this is going to be, at least seeing as we're starting from the origin, which is level to this point, what we're going to have here is a vertical displacement of 0. So I'm going to write that down. Again, I'll reiterate. So seeing as this, in this instance, we're starting level with the ground, by the time we've got over there, our vertical displacement will be 0. Okay, so that's a nice way to figure out where that is, because we can set s to be 0, resolving upwards, and then use one of these to work out something like a time. Great. And then a distance as well. It tends to ask about distance along the ground. You can then use this formula up here, but we've already talked about that. Okay, I think that's enough to be getting on with for now. We haven't seen any numerical examples yet, so I think the best thing to do is dive into an exam question, which is going to be a lot of fun. There's two I want to have a go at with you, which you can make notes on if you wish. And I'm going to set some extra practice questions for you to have a go at for the remainder of the day. So take a screenshot, make some notes, and then we'll move on to some practice ones, and then we'll call it a day. Okay, so this is from the Madas Maths website, which I'm going to give you some more questions from. Question 1 and 2, I'm going to go through myself, and I'll leave you to do some more. So, question 1. Bearing in mind that you won't be given a picture most of the time, and if you don't have one, best thing to do is draw one, as we've got in the solutions. So let's have a look. A particle is projected from a point O on a level horizontal ground with speed of 28 meters per second at an angle alpha to the horizontal, where tan alpha is 3/4. Now, it's worth noting to you again, we don't particularly need alpha itself as an angle. What we need to do in order to get started is the values of sine alpha and cos alpha. So as well as drawing a picture, it's worked out sine alpha and cos alpha by drawing a right angle triangle, which you can easily do. So if alpha lives in there, you can use tan alpha as 3/4 there and there. That's going to be the hypotenuse of 5 using Pythagoras, and then you can get sine alpha and cos alpha from there. Great. Okay, so here's our picture. Alpha goes there. 28 is our velocity, okay, coming out at an angle. We're going to want to resolve in our horizontal and vertical directions first. And then it flies over there, and then it says it moves under gravity and reaches the ground at point P. So that's all in the picture. Right. What I'm going to do then, I'm going to resolve and split into my separate components. So this part over here is going to be Vx, which is going to be 28 cos alpha. Okay, if you want to, you can use the fact that cos alpha is 4/5 and get that as a nice rational number, but for now I'm going to leave it and maybe work it out at the end. The vertical part up here That's Vy. That's going to be 28 sine alpha. And again, you can work that out as a fraction if you want to, because you know that sine alpha is 3/5. Okay, let's get started on the question then. Find the time it takes the particle to reach the greatest height above the ground. So bear in mind that's up here where we want to be. And we said this is the point where the vertical velocity component is going to equal 0. So it's doing that. It's resolving vertically, and it's using v equals u plus at, because that's the one that's best going to fit the information that we've got. Okay, if you want to write suvat and fill in all the values, I think that's probably a good idea, because it kind of suggests to you which is the best equation to use. So t is what we want. A is negative g, remember, because we're resolving upwards. V is going to end up at 0 at that point, and u is vertical velocity, 28 sine alpha. Okay, so sticking it all in your equation, you can do some suvat magic and solve for t, and then t ends up being 12/7 seconds, which is about 1.71 seconds. Great, okay, so far so good, all right? It's basic suvat, just using this kind of new theory of projectiles. Hence, part A is done. Hence, determine the distance OP. So the distance OP is the distance from here across the ground to there. What we've done so far might help us. So we've worked out a time to get to this point in the middle, which is the halfway point. And we know that because parabolas are symmetrical. Okay, you can always assume that if it's a nice parabola like this, it's symmetrical. So the time to get halfway will double to get over there. So we're going to double the time to get to the time taken to get to P. That's 24/7. Then resolving to the right horizontally, we're using our nice, easy, constant velocity formula. Distance is speed times time. The distance is what we want. The speed is 28 cos alpha. The time is worked out there, 24/7. And then we work out 76.8 meters. And we're done. Okay. Moving on to part C. The particle reaches a height h above ground 1 second after leaving the origin. So after a second, we're going to get to a particular height, which we don't quite know yet. We know it's before we get to the middle, because the middle is at 1.71, so it'll be somewhere over here. And we want this value of h. So it makes sense to resolve vertically, because we're after a height. Then our time is 1 second. Our acceleration is always going to be minus g. And our vertical velocity at the start is 28 sine alpha again. And then s is what we're after, because that's the vertical displacement. So bish bash bosh, stick your numbers in, work out s, and it's 11.9 meters. Okay, so it's still basic suvat, and we're done. Now for the next part, I think you might have done questions like this previously, but not with forces at an angle. I think you've done vertical and vertical motion only for this kind of question. But we want the length of time for which the height of the particle above the ground is greater than this h. So I think best thing to do now is get a new picture that kind of shows clearly what we're talking about here. Now I don't know why it's not clearing my annotations as I have one more go. There we go. Right, I'm going to get rid of this picture. Our new picture here is showing what happens at this height. T equals 1. That's our first answer here. And then at some other point, it's going to come back down again and reach the same height before falling back down to the ground. And we're after the length of time in this in-between stage where we're greater than this height h. So what we're after is we're after the other time at which we're at this height of 11.9. We're resolving vertically here using the same equation as before. Replace s with 11.9, that's our height. All the other information goes in, and we can get a quadratic equation for the time. Now, when you're solving your quadratic equation, you can either try and factorize it. A lot of these are going to be nasty decimals, so it's going to be quite difficult to do that easily, but you're welcome to try. If you want to use the formula, you need to show you're working. So I'm going to make a note of that. I've seen lots of marks lost where people are using the formula and aren't showing anything at all, or they're not showing enough. So a formula with clear working, please. So quadratic is reached, you solve it. T is 1 will be one solution, but we know that because we know it's 1 second to get to that point. The other non-trivial one here is the one we want, and that's 17/7. So we've now got 2 times to get to these points. The time taken in between them is obviously going to be the difference, which leaves you with 10/7. And we're done. Okay, so that's a pretty typical question. There are more to this. We're going to eventually be looking at doing this with vectors. And we're also going to see some questions where we're not actually starting at the ground. But for now, that's a kind of good idea as to what to expect for a question. Right, we're going to move on to question 2. Okay, so it's a very similar setup, but some extra things to kind of consider. A particle is projected from a point on level horizontal ground with speed of 45.5 meters per second at an angle beta. Tan of beta is 12/5. Okay, so again, we are finding out our sine beta and our cos beta. Draw a triangle if you don't believe me. Moves under gravity, blah, blah, blah. It reaches the greatest height of h above the ground and then lands at P again. Okay, so similar setup. Okay, so let's think about what it's asking us for this time. It wants firstly the flight time of the particle. And by that, it wants the time taken to get from start to the ground, because we're kind of assuming that it's going to kind of hit the ground and stop. Okay, so vertical motion then. We're looking vertically, because what we can do is we can set our vertical displacement equal to 0 here. We said that level with the ground, we're not changing our vertical height, so we might as well make S be 0 vertically. U is going to be 45.5 sine beta, which is our kind of vertical leg of this triangle. That's going to be 42, which is quite nice. And T is what we want because we're trying to get over to there with a time. There's our equation. Suvat, solve your equation. That one's a bit easier because there's no constant term, so you can factorize it quite nicely by taking out T. T is 0 will be one solution, but that's clear because we started at the origin, so that's T equals 0 to get to there. And then the other answer is the one we get over here, which is going to be 67ths. Okay, part B. Hence is a good word because it tells you that you can look ahead to what we did before. Determine the distance OP and the value of h. Okay, so horizontal motion is our favourite because it's constant velocity. We can do speed times time, and thankfully we've worked out a time already. So our horizontal speed is 45.5 cos beta. Time is 67ths. Times it together and you get 150 meters. Okay, so again, it's a bit like the last one. There we go. Right, now there's a couple of ways to do part H. It says using symmetry, which means we can halve the time if we like. We can work out our height after half of this time, or we can do it kind of from scratch if you like. It's up to you, but this is doing it by halving the time. So time is 37ths seconds, because it's half of 67ths. Minus g for acceleration. 42 we worked out is our vertical velocity, and v is 0, remember, because we're at the midpoint up here at the maximum height. And then again, we can use some Suvat. That's the best equation to use. Plug it all in and we get 90 meters. Either of these are going to do. The other way to do it is to do u squared plus 2as, and that doesn't have to involve time. So there's two ways to do that, and you can decide which one is your preferable one. Okay, for part C, the speed of the particle 4 seconds after leaving the origin. So bear in mind that speed is a scalar quantity. But to work out this scalar quantity, you're going to need both components of your velocity. Okay, we are very much treating these questions as if we're using vectors because we're working in 2D. Okay, so I'm going to, again, hide this picture. We're going to see what that kind of looks like that. And then we can work this out. So 4 seconds, and I want to know what we get for our velocity in both directions, okay, vertical and horizontal, because then we can build a triangle. So here we go, vertical motion. U is 42, that's from the previous page, that's our velocity times sine of beta. Time is 4 seconds, obviously, and v is the thing that we're after. So using a very quick bit of Suvat, again, v is u plus at will work. You can get a vertical velocity of 28 meters per second. Okay, so then at this particular point in time, after 4 seconds, our vertical velocity is now 28, and the horizontal, you notice, is what it always is. Okay, it's always going to be 45.5 cos beta. It never changes, and that's 17.5. That's, if you like, our vector version of velocity with the directions on. The speed, therefore, is given by the hypotenuse of these two components. So with Pythagoras, you can work that out, and the speed is then the number 17.72 meters per second. Okay, I think those examples are pretty good to be going on with so far. In next lessons, we'll be looking at kind of slightly harder ones. We'll move on to vectors. And then finally, we're going to derive some formulae, which is a whole bunch of fun. Okay, hopefully that was enlightening, I guess, and you learnt a lot there with some mechanics. If you've got any more questions, please give me an email. I'll get back to you. And best of luck with today's work. Okay, thank you, Year 13. I'll see you soon.